Hey everyone, this video is going to be on how to use CalcPlot3D to look at first and second order partials. We'll even talk about the mixed partials, fxy and fyx. So it's not perfect for these, but it will help you visualize them if you know what you're doing. So hopefully this will help you understand that. So I'm starting here with just our standard paraboloid or bowl shape. So this is z equals x squared plus y squared. What you want to do is go to show/hide 2D trace plane. And then we're going to go to the drop down menu. This is actually the same thing we used for traces back in like my first content video, and show fx trace/tangent line. So here we'll just want to use some point. You can either click on the grid, or I'm actually going to use the point -1, -1. Click enter, and that's over on this side. Now, I can see this okay, but especially if I move it over here, the red against the purple is not going to be great. So what I'm going to do real quick is go down to my surface, click the little gear wheel, and hit constant color. Red definitely does not go with red very well. This will show some good contrast. So this will help. Now I'm going to scroll back up, and I want you to notice that up here, you can see fx, or your x partial, at -1, -1 is -2. And this is exactly the slope of this black line. This is the tangent line along that trace, right? The x trace. So fixing your y at -1, but allowing x to move. And this has slope -2, which we can see. This is pointing downward. So then if you want to see it at different points, you can mess around with your sliders, right? So if I move around, so around x equals 0, or when we cross the y-axis, then we're seeing our partial derivative is 0. Then we see our slope, or our tangent line has positive slope, and we're seeing positive numbers here up at the top. And so this is how you can look at fx. You can do a very similar thing for fy, right? Just show fy trace/tangent line. Now we have a y trace where we're fixing our x value, but we allow y to change, and then you can look at different y values or whatever. If you want to look at second order partials, well, this time we have fy, and so we're looking at concavity, right, in the y direction. We see this is concave up the whole time, so we should expect fyy to be positive. What that really means is that fy is increasing. And so we'll notice as we keep our x fixed, but increase our y, we're seeing an increase in these values. So see, I go -0.64 to 0 to positive, right? I'm seeing increasing slopes in the y direction as I increase y. And so that is telling me that I'm concave up, or that my second order partial there is positive. Now, if you wanted to look at fyx, that means we still want fy, but we should view it as x changes. So let's stay on the picture. We're still doing a y trace, but now we're looking at different x values. So we're actually moving this along. And if you notice, all of these are the same. That's because this slope in the y direction here is slightly positive at 0.7854. And that slope actually stays the same no matter what x value you are at. So this is not a very interesting example for that one. If you want to see one that is slightly more interesting, this is one that has a saddle point. So I did x squared minus y squared instead of x squared plus y squared. So here, if we add in our fx trace/tangent line, and then, I don't know, just pick a random point over here, then as we increase x, here, let's actually bring this over to the other side so that increasing x looks like I'm actually going in the right direction. So as we increase x here, we see increasing values, -2 to -1 to 0, etc. And this is because, again, we're concave up in the x direction. On the other hand, if I look at fy, I'm concave down this way, right? So here I see downward concavity, and as I increase y, I'm seeing the numbers decrease here. as I increase y. And so that is what we should expect. Unfortunately, this is still not a very interesting example when it comes to the mixed partials. So if I change x, again, note that my fy is the same everywhere. So we can look at this last example, and this is actually just the default surface. So again, going here, I'll just look at fxy. So we'll show the fx trace, and let's do it here-ish. And yeah, that seems like a reasonable value. Maybe we'll increase our x ever so slightly here. Okay, so what we want to look at here, if we're looking at fxy, we care about our fx, but as y increases. So let me just pull this back this way. So notice that my fx slope, let me rotate this a little bit. So this is my positive x direction. So I have negative slope here, my negative 0.7, and increasing y is going off to the right in my picture. So as I increase y, what happens here? I'm noticing a decrease, right? I'm getting more negative with this slope. It's getting steeper negative. So this is that twist idea. So here my fxy is actually negative. I have a negative slope that is getting more negative or decreasing. So fx is decreasing as y increases. My fxy is negative. And then I'm going to hit this point around here where you're going to notice that it's no longer decreasing, right? So here I go negative 1.2. Oh, interesting, right? So negative 1.1 to negative 1.2 to negative 1.3. I kind of hit this peak in the y direction, and then I start to go down again. And notice that this is getting less steep. It's actually flattening out, and this is more noticeable over here. So as I continue to increase y, I'm getting flatter and flatter. I'm getting less negative. And so here my fxy would be positive on this side of the hump. Okay, so hopefully that helps you visualize these things. Again, the drawback to CalcPlot3D here is that it doesn't display a second order partial value, but by using the sliders, you can kind of see what's going on with your second order partials.